So, what is everything really made of? I mean, everything. For millennia, that question has been one of the biggest mysteries out there. But look, this isn't going to be a dry history lesson. No way. Think of this more like a multi-century detective story, a cold case file, tracking down the universe's most wanted, most fundamental suspect, the atom. So, let's open that case file.
Our investigation, believe it or not, starts over 2,000 years ago in ancient Greece. And the first lead in this massive cold case wasn't a piece of evidence you could hold. It was just a revolutionary idea wrapped up in one single powerful word, atomos, which basically means uncuttable or indivisible. So, on one side of this debate, you had the investigator Democritus. And his theory? Well, he thought everything is made of these tiny, solid, unchangeable particles, atoms, just moving through empty space. A pretty brilliant deduction, right? But his theory had a huge rival, the much more famous philosopher Aristotle. He came along with a totally different idea, that everything was just a mix of four simple elements: earth, air, fire, and water. And Aristotle was such a big deal, his influence was so massive that his theory just won. And just like that, the atomic case went cold for almost 2,000 years.
So for 2 whole millennia, this was it. This was the entire suspect profile. A simple, featureless, solid little ball. An atomos, something that you absolutely could not break down any further. It was basically a philosophical ghost, just an unproven idea, sitting there, waiting for someone to find some real evidence.
Then, fast forward to the 19th century, and boom, the case gets dramatically reopened. You have investigators like the chemist John Dalton, who noticed that elements always combined in these neat, fixed ratios, almost like they were made of little individual packets. Then physicists like Maxwell and Boltzmann realized they could explain how gases work by imagining them as just collections of tiny, billiard ball-like particles. Now, the evidence was all circumstantial, but it was really starting to pile up. The atom wasn't a ghost anymore. It was now the prime suspect.
But here's the twist. Just as the atom was becoming the main suspect, a whole new mystery pops up. Was this indivisible sphere really indivisible? Well, the first major breakthrough in the case was about to blow that idea wide open.
The key was this strange glow that scientists were seeing in vacuum tubes. They called them cathode rays. And our lead investigator now is J.J. Thomson. He had one crucial question he needed to answer. Were these mysterious rays some kind of light wave, or were they a stream of actual physical particles being literally ripped out of the atoms inside the device?
Thomson was super methodical about this. First, he showed the ray traveled in a perfectly straight line, just like a particle would. Okay, step 1. Second, he brought a magnet near the tube and the beam bent. Now that is a huge clue, because light waves don't do that, but moving charged particles, they sure do. The final, undeniable piece of evidence came when he used an electric field. The beam bent toward the positive plate, proving once and for all that whatever these little things were, they carried a negative charge.
And the conclusion from all this? Whoa, it was absolutely earth-shattering. These rays were made of particles. They were negatively charged. And, here's the most critical part, they were exactly the same no matter what material he used in his experiment. He had discovered a fundamental piece of all atoms. He originally called them corpuscles, but today we know them as electrons. The indivisible atom had just been divided.
So this discovery meant they needed a whole new suspect profile. I mean, atoms are neutral, right? So if they have these negative electrons inside, there must be some positive charge to balance it all out. Thomson proposed what we now call the plum pudding model. Just picture a hazy sphere of positive charge with these tiny negative electrons dotted inside, kind of like plums in a pudding. For the very first time, the atom was seen not as a simple ball, but as a complex object.
All right, so the plum pudding model was the leading theory. But a brand new investigative tool had just been discovered right around the turn of the century: radioactivity. And this powerful new weapon, which literally shoots tiny particles out from the atom itself, was about to be turned on the atom. And what it would reveal was a shocking, frankly impossible truth.
Okay, so the investigation now moves to the lab of a guy named Ernest Rutherford. His team decides to test this plum pudding idea directly. The plan was pretty simple. Fire these heavy, fast-moving things called alpha particles, which are positively charged, at a sheet of gold foil that was incredibly thin. Now, according to Thomson's model, the atom's positive charge was all spread out, like a thin mist. So what did they expect to happen? Well, these big alpha particles should just tear right through the foil, like a cannonball through a piece of tissue paper.
But that is not what happened. Not at all. I mean, sure, most of the particles went straight through, just like they thought, but a few of them were deflected at really wide angles. And get this, to their total astonishment, about 1 in every 8,000 bounced almost straight back. Rutherford later described just how stunned he was with this amazing line. It was as if he had fired a 15-inch shell at a piece of tissue paper and it came back and hit you. This result was it was impossible with the plum pudding model. There's no way. The only way a heavy alpha particle could get knocked straight back is if it slammed into something incredibly small, incredibly dense, and also positively charged. The old theory was dead, case closed. And this incredible discovery gave birth to a brand new, evidence-supported theory, the nuclear model. All the positive charge and pretty much all the mass has to be packed into a tiny little core at the center, the nucleus.
So this shocking verdict gives us our final updated suspect profile, a profile that would completely change how we think about solid matter itself.
To really get your head around this new model, you need a whole new sense of scale. So imagine this. The nucleus is like a tiny pinhead sitting on the floor right in the center of a giant cathedral. The electrons, they'd be like microscopic specks of dust just swirling around way, way out in the vast empty space of the dome. The atom isn't a solid pudding at all. It's an almost entirely empty cathedral.
And that leads to a really stunning implication. The chair you're sitting on right now, the screen you're looking at, even your own body, all the stuff that seems so solid, is actually made of almost 99.99% empty space. It's all just held together by invisible electric forces. Wild, right?
So it seems like the case of the atom structure is closed. We've got our suspect profile. But here's the thing about science. In solving one mystery, Rutherford's team had accidentally opened up a much deeper and way, way stranger one.
Our investigation really took us on an incredible ride. The suspect's profile went from just a philosophical idea to a solid little sphere to that complex plum pudding and finally to this evidence-backed nuclear model. I mean, it was a total triumph of experimental physics. But this final model had a fatal flaw. You see, according to the laws of physics they knew at the time, an orbiting negative electron should be giving off energy. It should spiral into the positive nucleus in like a fraction of a second, causing every single atom in the universe to just collapse. So why doesn't it? Why is all this stuff around us stable? That question couldn't be answered by this model, and solving it would mean opening a brand new case file, the bizarre and revolutionary investigation into quantum theory.